Okay, welcome back. Well, in this problem, we've got a highway and we have a police car. Woo! Put a little siren on there, maybe even make it a little red. And we've got a motorcycle. Yes, let's make it a kind of like a super bike kind of thing. That's hard to do, but okay. And a person on the motorcycle. And now this motorcycle is traveling with a constant velocity of 200 kilometers per hour. Whoa, that's definitely over the speed limit. Illegal. But the police car is traveling with 100 kilometers per hour. They're observing the speed limit on the highway. But you see, something happens. The motorcycle is totally oblivious to the police car because, well, why else? He's probably texting. So once the motorcycle reaches the same position as the police car goes, uh-oh, I better accelerate and catch that criminal. So the acceleration of the police car, P stands for police, is equal to 3 meters per second squared. But his initial velocity, this is the initial velocity of the police. This velocity is the velocity of the motorcycle, and it's also constant. In other words, the motorcycle neither speeds up or slows down. Question: when and where? When and where will the police car, when and where will police catch the motorcycle? Question mark. Now, in order to figure this out, first of all, let's draw a little graph here. And this is a graph of D versus T. Okay? And if you'll notice, the initial velocity of the police car is 100. So obviously they're not starting from 0. Therefore, the slope of this police car, let's make the police in red, is not going to be 0. But in fact, whoa, I didn't do that exactly right, but close enough. That's the police. Now here's the motorcycle. The motorcycle really isn't accelerating. They've just got a straight line. At that point, they intersect. That means at that point, they have the same position, and that is where they get caught. So if we draw a line there, and a line there, this is the position we are seeking, and this is the time that we are seeking. Now the way we're going to do this is we're going to identify what are the two types of motion. The motorcycle, as you can see here, is traveling with a constant velocity. Therefore, delta D of the motorcycle is equal to Vt. That's constant velocity equation. However, the delta D of the police car is not constant. They are accelerating, as you can see here. So therefore, here is the AP police, T squared plus VIT. That is the equation for the police car. Now, obviously, at this point, what we have to realize is that, in fact, delta dm is going to equal the displacement of the motorcycle starting from where? Starting from this location. So this dotted line is 0. This is the location and time when the police car actually starts accelerating at 3 meters per second squared. So this is the displacement of the police officer. When does this, what point in time is this location? It's when delta D police is equal to delta D motorcycle. That's the definition when those two graphs intersect. So now what we do is we say, all right, what is that? That's just Vt, V motorcycle, this is an M, is equal to 1/2 acceleration of the police time squared plus initial velocity of the police times time. And what time is this in this equation? Well, it's this time right there. So let's solve for it. Fortunately, this isn't so bad. It's not as ugly as it seems, because the way we would do this is we would simply go divide everything by t. And so those t's cancel out, and what we're left with is Vm equals 1/2 APT plus VI police. And solving for t in this problem, well, we can take this term and take it to that side, but would have to be negative, so the whole problem turns into that. Now we have to isolate t, so therefore we're going to multiply both sides by 2, get rid of this 1/2, and divide by AP. Let's do that all in one step. So we'll go 2 times Vm minus VIP divided by acceleration of the police, that's time. Now if we plug in our values at this point, and we can do that now since we've solved for it algebraically, 2 times, now what was the velocity of the motorcycle? Well, if we come way back up here again, we see, aha, it was 200. And the initial velocity of the police was 100. But if you'll realize, though, those values were in kilometers per hour, so we can't really use that. We have to convert it to meters per second. And the way of doing that, of course, is to divide by 3.6. So motorcycle 200 divided by 3.6 minus initial police velocity, which is 100 divided by 3.6, and we divide all that by the acceleration of the police, which is 3 meters per second squared. And by the way, bad me, I actually forgot the units here, and that's meters per second. And so therefore, when we put that into our trusty calculator, we get an answer of 18.5 seconds. Yay, we've solved half the problem. So this location here turns out to be 18.5 seconds. But we still don't know the position. Now we have a choice. We can either use this equation, or we can use this equation to solve for the position. As I'm sure you can see clearly, this one is going to be more work. This is a simple equation. All I have to do is multiply two things. I'm going to take that one. So solving for delta D motorcycle, that's going to give me, again, 200 divided by 3.6 meters per second, and multiply that by the 8 time of 18.5 seconds, and lo and behold, I'm going to get, I think it was something like 1028, something like that, I think. Either 1028 or 1026, I can't remember. Anyways, it doesn't really matter because I'm just going to round it anyways. We'll say 1026. Now that's in meters, but in fact, I'm going to express this in kilometers now. So that's going to equal 1.03 kilometers. Yay! So there's our answer. It's going to take, at this point right here, 1.03 kilometers and 18.5 seconds for the police officer to catch up to that motorcycle. Okay? That's it. That's the end of this problem. Hope you enjoyed it. See you next time.